Hello everyone, today we're going to go over the concepts of connectedness, compactness, and Hausdorff spaces in topology. Now, these are three key elements of topology that will be very useful in the future. So it's going to be very nice to have a great understanding of what each of these terms mean. So let's start. What is connectedness? Now there is some intuitive idea of what it means for something to be connected. So if you have some space that's connected, it's in one piece, right? So say I have some sphere, okay? Like an actual 3D ball sphere that we know and love. Now, this sphere is connected, right? We say that each point on the sphere is connected to the next point that exists on that sphere. And in fact, each patch on the sphere is connected to the very next patch that exists. The sphere is all in one piece. There's no holes or anything. However, if I had some plane, and I had a hole in the middle of the plane, this plane is no longer connected in one piece, because this point over here is not connected to this point, to the very next point on the plane. There's a big hole in the middle of the way. Same with each patch on the plane. So this is not connected. Now what we want to do is we want to capture this idea rigorously in topology. So let's start. So we said that a topological space, xt, is connected if two open sets if there does not exist two open sets such that the intersection of those open sets are the null set and the union of those two open sets is the set X. Okay? So this is saying that we have, X, the topological space, this entire space, not just X, but the topological space, is connected in one piece if it's defined as if there does not exist. So there does not exist two open sets such that the interval between those two open sets is the null set, and that's important, and the union of those two sets is X. So if we cannot find two open sets that obey these properties, then our topological space is connected. Okay? So let's actually show how this definition captures the idea that we wanted above. So say I have some set X. Okay? I have some set X. And in this set, we would say that this set is connected. Sorry, this should be in one piece. So we would say that this set is connected, right? And it's connected because say you have two open sets. So these are open sets A and B. Now we can say that the union of these two open sets is the entire set X. However, the intersection between these two sets is not the null set. Instead, it's this river-like structure that runs down the middle. That's the intersection of those two sets. I haven't defined a topology. Typically, I would have to define a specific topology to be more concrete. But you guys get the notion of what I'm saying. Also, this boundary should actually be dotted lines. It's an open set, right? So we have two open sets A and B, and while the union is an X, the intersection is not the null set. They are not disjoint. So this will be a connected topological space. I might go, oh wait. If I have open set F an open set G, they're disjoint, right? Therefore, X is not connected. Well, I'll be wrong, because remember, to be connected, there must not exist A, B that are not only disjoint, but the union is X itself. The union of F and G is not X. So while open sets can be disjoint, as long as the union of them is not X, our space is connected. Now here's an example of a space that's not connected. So say I have this set over here, okay, set X. Now here I have two islands, A and B. Again, these should be dotted lines, I forgot. Now A and B are clearly open sets. You'd have some topology that we'd have to define, but A and B are open sets, okay? And we see that the union of A and B is actually the entire set X. And the intersection between A and B is a null set, right? They're not connected. It's a null set. And since there does exist open sets where the union is X and they are disjoint, then this space is not connected. So that's how it captures the idea that we wanted at the start. This idea of not having disjoint open sets that union to the entire set captures the idea that we wanted. Now let's define some more terms here. Let's define what it means to be disjoint. I'm using the word disjoint, but I haven't really defined it yet. So to be disjoint, so disjoint sets, those are defined. So sets A and B are said to be disjoint if the intersection between A and B is the null set. So if you have two sets, and the intersection is the null set, they're disjoint. That captures the idea of like the colloquial disjoint, right? Let's also define what it means to have a separation of a set. So a separation of a set is defined as if there exists open sets A and B, sorry for the noise, such that the intersection between A and B is the null set and the union between A and B is the entire set, then A and B are said to be the separation of the set. So that's what we call the A and B islands, basically. It's also this is also sometimes called the separated sets. They're also sometimes called that. Now, intuitively, a disconnected space is just the opposite of a connected space, which means that there does exist an A and B that are open sets such that the intersection is a null set and the union is X. That's a disconnected space. However, to be a connected space, there must not be those elements that satisfy those two properties. Yeah, that's what that's the concept of connectedness in topology. Now let's talk about what's next? Compactness. Okay, yeah, compactness. So, compactness, the definition is a bit more winded up, but compactness basically it's defined as the following. So, our topical space, should be xt, is it's said to be compact if for every open set So for every open set, so if for every open set where the entire set, sorry, wait, how should I define this? Alright, so the topological space is compact if for every for every set of open sets where the entire set is contained in the union, the infinite union of these open sets, there exists some set KL such that KL is a subgroup of those set of open sets, and X is a subgroup of a finite union of those subsets of those open sets. Okay, so basically P has to be an actual number. So this is a bit convoluted. So I'm going to break it down a bit. So this is what it's saying. So we would have some open sets. Remember that an open set is just a member of the topology. Or topology might look like this. It might have this is the example I'm going to give right now. It's not going to exactly be a topology, but I'm just trying to give you guys an idea of the topology. So our topology might be like say A, B, maybe like A, and then like B. All right, and like the null set as well. Oh, and the set X, entire set X. Okay. And that's our topology. And our space is compact if for every set of open sets. So an open set is defined as a member of the topology. So A, B, and X, those are open sets. So if for every for every set of open sets, right? For example, A, B, and A. So let's call it G. That's a set of open sets, right? So if for every set of open sets, the entire set X, now note that G doesn't have to be an X, right? But saying that for the entire set X, it's contained when we take an infinite union of these open sets. So what I'm saying is, we have a set of open sets, right? So we can have G is this. We could also have H is B, and then set X, right? So here I have a set of open sets, and it's basically saying that, okay, for all of these set of open sets, I can take the infinite union of these set of open sets, and X should be contained in those union, in that union, basically. Now for the more intuitive, I know this can be a bit abstract, so let's just give a picture, a pictorial. So here I have my set X, okay? Set X. It's basically saying, now I can have, take a union of a set. So like each of these dotted pictures will be an open set, right? So and you can take an infinite union of all of these open sets. You get them all together, all of this together, and X, the entire set X, has to be contained in that union. Well, that's the first part. So it's saying if for every set of open sets, the entire set X is contained within the infinite union of these open sets, there exists some subset of those open sets, right? where X is also contained in that subset. So I have, so it's basically saying that it's compact if for every open covering there is a finite subcovering. That's like the more shorter way to put it. So it's saying that like here are my two open sets. So this entire thing. So I have a set of open sets for G and H, right? And if for every set of open sets there exists some subset of that also covers X, then our topological space is compact. So here's an example. Let's say I have J is set J is A, B, it's also A, and it's also B, okay? So I have a set of those open sets, okay? And so here, so I have a set of open sets, and I have a subset, let's call it subset K, which is it's just going to be A, B, and A. Now, if that subset, if I can take a finite unions of these subsets and it covers X, then my space is compact. So let's go back to our picture. Let's try a new picture actually. So here's X again. So here might be the union of multiple open sets, okay? It might be a union of multiple open sets. Should be dotted lines, but I'm a bit lazy. So this entire thing is like unions, all these balls you see here, they're unions of open sets. And we can all agree that X is contained in that. However, if there is some subset of these open sets that also contains X, like if there's some finite, if there exists some subset of these unions that's finite, that also can, if there exists finite unions of this entire open covering that contains X, then XT is the topological space. And we see that's true. Like this one over here, 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 this one over here. We can union all of these things up together. This one over here as well, and it's contained in X. So it's. I know I'm explaining this the best I can, but it's basically saying that okay, I have the set of open sets, right? And I union these together, and I get X. I union all of these together to get X. And if I union them, I get X. If I could take a finite union of those open sets to get X, then boom, XT is a topological space. Should have said that right off the bat. So it's just saying that it's saying that if I have a set of open sets that X is a subset of, if I have an infinite union of sets of open sets that X is a subset of, and there are a finite number of unions of those open sets that X is also a subset of, then XT is a compact space. That's what it means. So I hope that you guys can understand what I'm speaking of here. Probably could explain that better, but yeah, that's what it is. Lastly, we have a concept of a Hausdorff space. This one is going to be much more easier to explain. Hausdorff. Almost every space is a Hausdorff space. At least the ones that we are going to encounter. So the Hausdorff space is defined as so basically XT is a Hausdorff space if there exists, yes, if x, small x and y are in X, there exists some neighborhood around X and some neighborhood around Y, such that MX and MY are disjoint. That's what it's saying. So, I forgot what neighborhood is. Let me re-jog your mind. So, it's basically, so I have some point X, and I have some point Y. A neighborhood around X is just some set where there exists some open ball around X that's contained in that set. So, I might have, some set, like MX, there does exist an open ball around X that is contained in MX. So then MX is a neighborhood of small x, okay? And then it goes to form a neighborhood of y. It's basically saying, well, it is saying that if there exists a neighborhood around x and a neighborhood around y, such that the intersection is the null set, then my space is a Hausdorff space. So there just has to exist like some neighborhood around x and y that are disjoint. Now this, like, almost every space is a Hausdorff space, right? So for almost every space, I can have a neighborhood around x, a neighborhood around y that are disjoint. Now, also know that an open ball is a neighborhood, since as long as an open ball is contained in the neighborhood, then the neighborhood is a neighborhood. But an open ball is obviously contained in itself. So I can really reduce this down to saying that I have 2 points x, 2 points y, an open ball around x. It's saying that it's saying that if I have a space where the open balls around x and y don't, like, there exists some open ball around x and y that don't intersect, boom, you have a Hausdorff space. And obviously, like, the real number, like the R2, the R2 plane will be a Hausdorff space. Since if I have 2 points x and y, I could always form some open ball that isn't connected to each other. Even if we're like really, really, really close to each other, just really close, I can form an open ball just so small that they don't connect. Like, they could be a billionth of a meter apart. I can still make my open balls for x and y so small that they don't intersect. And if I create every single space that is a metric space, it will always be a Hausdorff space. Let's prove that. Let's prove it. Okay? So we want to prove for every metric space, sorry, not every, it's in every metric space is a Hausdorff space, space. Okay, every metric space is a Hausdorff. Let's prove that. Okay, so yeah, let us start. So first of all, let's try to break this down a bit. So all we have to prove is that open balls around x and y, where x and y is in some space, is in some metric space, the open balls are disjoint. That's all we have to do. So we can like, there exist some open balls around that are disjoint. So we can actually prove this by proof by contradiction. That's what we're going to use. Proof by contradiction. So let's actually first of all, amazing sentence. Okay, so how are we going to prove this? Well, let's make some epsilon radius, where the distance between x that equals the distance between x and y divided by 2. So here I have x, here I have y, and I have some distance between x and y, right? And divide that by 2, that's epsilon. And that actually forms an open ball around x and it forms an open ball around y. Also note that here I should have noted that x does not equal to y. BT dubs. So there is an open ball around x and an open ball around y. Let's note that as open ball x epsilon, the open ball y epsilon. So now let's suppose, I think we can all agree right off the bat that these are not, that these are disjoint, because the intersection between these two sets is nothing. We can't say it's epsilon because epsilon isn't contained in the open ball, right? In either of these open balls, right? And this is general. I didn't pick any metric here. This is really general. We've pretty much intuitively shown that there will always exist an open ball that is disjoint. But let's actually but let's get back to the proof. So let's assume that these two balls are not disjoint. Let's assume that the intersection between x and epsilon of the open ball around x and y, let's assume that is not the normal set. Let's assume that they are not disjoint. This means that there exists some epsilon that's inside both the open ball around x and the open ball around y, right? Because if they are if they're conjoined, if they're not disjoint, then that means that there's a shared point between those two balls by definition, right? Now, note that the distance between x and z has to be less than epsilon, right? And the distance between y and z has to be less than epsilon, right? Since for epsilon to be in x, to be in the open ball around x, and to be in the open ball around y, the distance between x and z has to be less than epsilon. Same thing with y, since that's in our definition for an open ball, right? Now let's actually bring about the triangle inequality. So distance between x and y is going to be less than, again, it will be less than or equal to, but for x is not equal to y, it's less than the distance between x and z plus the distance between z and y. And that is our triangle inequality. Now remember that the distance between y and z is just the distance between z and y due to one of our postulates of the metric, or the axiom of the metric. Okay? Now note that this has to be less than epsilon from here, and this has to be less than epsilon from here, which means that this entire thing has to be less than 2 epsilon. Okay? And now the distance between x and y, well, what's that? Well, if epsilon is equal to the distance between x and y over 2, this means that the distance between x and y is just 2 times epsilon. Okay? So now we have 2 epsilon is less than 2 epsilon, which is a contradiction. So we have a proof by contradiction. Saying that these two sets are not disjoint leads to a contradiction, which means that these two sets must be disjoint. They must be disjoint sets, which means that there will always exist in a ball or a neighborhood around x and y that are disjoint. Since we've proved in general case that there will exist some that's disjoint, specifically one where epsilon equals the distance between x and y, which is we've proven that they must be disjoint. So yeah, that's Hausdorff spaces plus a nice proof that we learned. So yeah, that's the 3 things that we are going to go over in this video. I'm extremely tired right now, exhausted. This is like my 4th take, or maybe 3rd take of this entire thing. So I hope you guys like this video. I spent a lot of effort learning this content and sharing it with you guys. I learned this to share it with you guys and to kind of improve my understanding of topology and stuff. So I really appreciate it. I know that all YouTubers ask for this, but I generally mean it. I really appreciate it if you guys like this video and share it as well. So yeah, that's all. That's all, folks. We have. I hope you guys have an amazing day. Have an amazing day. And now I'm going to pass out. Bye.